thank you, Fan, for organizing this. And I've been excited in the past few months by the energy and interest in rigs, and a lot of it's spurred by Tom's coming on board and designing an expensive hammer. That'll be a game changer, I think. I wanted to thank Jim Woodhouse and Evan Davis for helping me understand some of the underlying science, and also my team, Alex Curtin and Lonnie Marino, who were instrumental in the design and implementation of the equipment I'm going to be talking about. So I started getting interested in violin radiation measurements from Gabi in his lab back in the mid 80s. And it soon became clear that watching a measurement in process was the very definition of boredom. It was like an all afternoon project with checking wires and things going wrong. And finally you'd do one measurement, then a couple of days later, you'd see a graph. And that was fine. Gabi was doing serious science. He wasn't trying to create a workshop tool, but being a maker, I sort of had my eye on, well, how could I use this in my workshop? So in the early, about 2000 or 1998, I met Martin Schlesky. He gave a presentation on his work. And he was doing violin radiation measurements in the workshop using an impact hammer. And that was a relatively new tool on the, in the field. I'm not sure exactly when small ones came out, but they had an immediate and obvious use in violin research. So Martin had devised a system where he would tap the side of the bridge, and you can see him doing that. And there's a microphone, I think he had it 50 centimeters away. And he would also rotate the violin to get readings around the instrument, and then rotate the whole rig to try and smooth out some of the room modes. So I got very interested, and I got a hammer of my own. And I was also following what George Bissinger was doing, and he was freely suspending the instrument, more or less, by mounting on an elastic band. So I adopted that in this, one of the earliest prototypes from, this is 2004. And I took it to the Indianapolis International Violin Competition, and some of my colleagues will remember, we had the very good fortune of being able to spend a couple of hours during a jury lunch break with all 12 of their instruments. So there was just handfuls of Strads and Guarneris and things. And I had my rig along, so managed to measure them all. And that sort of gave me a taste of the possibilities of not doing laboratory quality measurements, but how much could one learn by quick measurements of instruments with the sort of equipment that you can actually lug to the instrument. Most instruments don't show up in labs or in workshops, and if they do, it's fairly rare. So you generally have to go to the hotel room or the backstage or the museum, and both Fan and Claudia have both shared a lot of time doing this sort of thing. So my goal was to make as good a possible measurement, as meaningful one and as repeatable one as was feasible for these sort of field conditions. And so it began. I don't know, maybe some years later, there was enough other interest in the rig that I made about, I think, 10 or 15 of them that were sold to makers and some researchers. And I got together with a furniture designer friend of mine, and he did a lot of beautiful woodwork. And that was a very satisfying project. As years went by, I found it would be nice if it was lighter. It was nicer if it packed smaller. And also I started measuring horizontal impact as well as vertical as well as horizontal measurements. You can hit the bridge from the side and you'll get one measure. You can hit it on top directly down, you'll get another. And that seemed to me important. So I think this rig here, you can actually swivel it to address both. And now in the past decade, amazing things have happened, both with the internet. You can find all kinds of parts easily that you couldn't before. And also there's been such an explosion in digital photography and such that there's sort of modular components that do all sorts of things. And so I've started more and more using those because they're relatively inexpensive and they're super stiff and precise and beautifully finished. So they really lend themselves to this sort of thing. You can always, of course, improvise things out of wood, but unless your time is sort of unlimited. It's really worth putting a little bit of money, I think, into some components. So let me review some of the basic stuff. Well, Tom covered this. The PCB hammer is more or less the standard one. It's expensive. The power supplies, to my mind, crazy expensive. And they're also, I really don't much like some of the design decisions they've made. I've talked to engineers there on why, and the bottom line is they don't have enough market that it's worth their while doing anything. So I'm even more grateful that someone else like Tom has come in who is interested in optimizing in some sense for the sort of work we do. As it was, the basic equipment you'd have now, you know, 1,400 for the hammer and power supply. You'd have a microphone anywhere from $30 to several thousand, and various cables, and then and then you need to put together a rig, something to hold the instruments. And my real working philosophy is you can't do a measurement in a few minutes, or you're probably not going to use it very much in the workshop if you're a working violin maker. It's just too much of a flow breaker to put everything down and set up an experiment. So I think the more dedicated and the more ready to go and plug and play we can get, the better. And if you're a researcher, it's a very different thing. Just a word about software. When I was starting, the only commercial software I could find that was reasonably affordable, and I don't mean MATLAB or some of the big ones, but this was Spectra Plus, which was a few $100s, and it would do a lot of the stuff. It wasn't particularly well. It was a general purpose program, so it could do a lot of things, but it was very slow to do the sort of measurements we were doing. Everything changed when George Stepani came along. Absolutely amazing that he wrote all this software, and I think it was a real game changer, and we've all benefited ever since. His was started with, was for modal analysis, but it also worked for radiation, a much simpler process, and he developed it a fair ways to make that very, very feasible. And then along came Chris Rogers, a Tufts University engineer who's very interested in violin research and is boundlessly enthusiastic and generous with his time, and a big thanks to him too. This is version, I think, 103. It's been 2 years now. I think we're up to 105 already. We're getting ready to have it as version 1. But it's been a fascinating process to try and design software where everything is where you need it, and you can keep all your notes there, and you can make lists of FRFs and pull them up quickly and do all sorts of analysis processes. And it's going to keep on evolving and basically based on what people want and what they can use. So I've had the notion that there's enough parts around now that if one were to design a rig and specify the parts, people could build it themselves. Maybe it's worth it. Maybe it's not. It depends on what you like to do. If you like building things, you probably want to do it. If you don't, you just want to get down to it, might be worth buying one. I still sell them, though I'm thinking of turning that over to Tom. He'd be great at that. At any rate, so this is a schematic. I didn't have time to take good photographs, but Lonnie put together the digital parts. And I put in white parts that are 3D printed. And when all this is done, we'll put them online and the, sort of the shopping list so that people can do it. So it's about $75 for the 3D printed parts. And all of this is commercially available photography parts. The $400 doesn't include the tripod. And then these 3 parts we milled in-house, but people could make either with a CNC machine or by hand. Indeed, that's very possible. One of the crucial things is being able to rotate the instrument smoothly, and it really helps to index rotation, meaning you can kind of click it into the new position, so you're always getting the the correct angle. This we've done after a number of prototypes. This seemed to work really well. there's a spring plunger in there that indexes into these slots. There's 24 around, so you can do 45 degree, excuse me, 15 degree changes, 24 measurements all the way around. Now that's really needs a CNC to make it feasible. So you can also buy these pan heads for cameras, which I was using on rigs for a while. They're beautiful and they're not expensive. This one's maybe $39. The only trouble is the clicking is nice, but it's not really strong enough for the kind of mass and leverage that the rig has, but they work pretty well. So one of the things I've changed in the last couple of years is instead of mounting the instrument on elastic bands, putting them on just some closed cell foam. It doesn't have a lot of damping. Now there's a couple of reasons for that. On elastic bands, the instrument tends to bounce around a lot. And if you're also wanting to do laser admittance measurements or anything like that, that's a real inconvenience. I found that putting these here steadied it a fair bit. Also, it leaves room behind and in front for chin rests and shoulder rests. So, if you want to do a test about how much effect does a shoulder rest have on the sound, you have to have a rig that lets you fit it in there. So that's one of the tweaks on this rig. It'll adapt to a lot of sort of clunky fittings that people put on their instruments. All these parts are milled out of Richlite, which is it's kind of a recycled paper epoxy resin, very sustainable, beautiful material that guitar makers have used for fingerboards for a long time. In fact, it's a very plausible fingerboard surface. It mills really nicely. It's easy to finish, but of course, one can also use wood or better still plywood, something like that. And at the top, this particular holder for the neck is easy. It's very two-dimensional. I put in another rubber band because it is conceivable an elastic band could break in use, in which case it's good to have a sort of a safety bit there, especially if you're the owner of the instrument is breathing over your shoulder and worrying about it. Now, this is the hammer bearing that works for a PCB hammer. We'll adapt it for the new hammer once it's ready. It's basically a needle bearing. There's a couple of set screws with pointed ends in there, and inside the printed plastic part is a brass tube, and they fit together. And I tried a lot of different bearings, including miniature, high precision ball bearing, you name it. And this actually is very simple, inexpensive to make, and it works super well. It's just a bit fiddly to get just the right amount of force, but once you do, it's very stable. It doesn't tend to vibrate side to side and other things which interfere with the measuring. And so all the printed parts here are made with a multi-jet fusion process with glass bead in them. And they're actually, it's a beautiful material. It comes out ready to go, a lovely sort of slightly fleckled finish. And it's very tough. It's not going to crack if you drop it. It's really wonderful. And this is the mechanism that allows one to rotate. There's a spring in there so that turn it around, it clicks really nicely at 45 degree increments. And the spacing from there to there means that when you rotate it, the hammer moves 7 millimeters over, which means you're in about the right spot to do the vertical tap. You could also arrange it so that the rotation was right around the center of impact, the point of impact, if you were doing different kinds of measurements. So you can see how it works. And this part was actually, this design, I've tried a lot. This is really sweet. It's a pleasure to stand there and click it for 15 minutes at a time. So these are the milled parts. And again, those are all perfectly susceptible to being done by hand. And then Lonnie did a little animation of this for fun. So I typically do 5 taps for each microphone position. Then the instrument is rotated through 12 positions, doing 5 taps at each. And then you back it around. And then I move it around and do 5 taps on the vertical at the highest point in the bridge. Oops. Where do I stop it? There we go. So for there's a lot of new names in the list, so I thought I'd just introduce some of the basics. This is a typical violin spectrum. It's the sort of thing you get from a violin measurement. You take the, well, to use Jim's term, the clunk, the instrument clunk, and you do a fast Fourier analysis of it, and you come up with the spectrum. And for terminology, there's A0, this lowest peak, the B1 modes, B1 plus and minus. It's a transition hill, doesn't show much on this instrument. A bridge hill shows very well on this instrument. These are just the horizontal measurements. Sorry, it's amplitude in decibels and log frequency. And I also use bands a lot because it's easy to tell sort of at a glance how much level there is in different frequency regions. And because I think a lot of sort of hearing is sort of band level related. Recording engineers are forever dividing things into 3rd octave bands and things like that, because you can hear those kind of changes. So the big question about any measurement process is it repeatable? And after a couple of decades of doing this, I sort of decided to better roll up my sleeves and really test this, because we've been doing it, other people have been doing it, people have been publishing stuff, but I've never actually seen anyone publish a test on how repeatable it is. So I hope to publish this in some form, probably for the VSA papers. So this is a fairly informal presentation. So first thing you have to do is to do a measurement, take the instrument out of the rig, put it back, and do it again, and do it again a number of times. This is, I think, I can't read the top of my screen because of Zoom. I think it's 10 successive measurements. This is 5 taps at each position, 12 of them around, and then take the instrument out, put it back, do it again. And so we see that there's some, plus or minus 1.25 decibel differences here with 2.5 dB, that's that spread. It's pretty good most places. What is good enough is the question. Jim Woodhouse, Evan Davis, they say plus or minus a decibel is what, it's hard to do a lot better in radiation measurements because there's so many complications with, you're not just tapping the bridge and measuring right there as you are with admittance or modal analysis. You're going through the air and there's reflections and all sorts of things to worry about. So it's not trivial to get the perfect measurement twice. So I think this is pretty good. The question is, how much better could it be, and what causes these? Why is it a problem? Why, for example, does it seem to get better at high frequencies when in fact the force input is lower there? I always say that don't sweat the details is about the worst advice you can give a violin maker. And I think I'm learning the same is true with research. It's really interesting to dig in. So I'm going to do that. So band average repeatability, it's about plus or minus 0.6, 0.5, 0.35, 0.15. It drops quite a bit with frequency. How good is that? Claudia Fritz published a paper, I think with some colleagues, about just notable differences. And she had a figure for Dunvold bands, which I've put up here. And it seems that players, I think, and listeners could hear at best 1 to 3 dB. Is that right, Claudia? So we're well within those. So the measurements can do better than the human ear in that limited sense. So obstacles to repeatability. One of them is sensor calibration and electronics. I'm not going to get into sensor calibration. That would be a huge thing, except to say that Chris has been working hard on making good calibration wizards, and it's doable. It would probably need makers coming to things like the Oberlin Workshop, bringing their mics and hammers along, and they'll have a laser there and some other jigs, and everyone can calibrate their sensors. Now, most of these things, like a good microphone and a good hammer, they don't tend to get out very easily. So once done, it's pretty stable. But the funny thing is, PCB always says should be recalibrated every year. I bought a microphone calibrator, a fairly good one, and it said it should be recalibrated every year. So it's an endless thing trying to get the perfect calibrations. But one thing that's important is the sound card. Now, the early sound cards I used had manual gain, so these two little knobs, and you do them to get about the right gains in both channels, and then you have to be very careful not to change them. So people who do this, who use these, tend to take the knobs off and put little clamps there so they can lock them in. That's a good idea. But some years ago, maybe 5 or so, Roland came up with Octacapture, and it was very well reviewed in the sort of prosumer audio literature. It was it's about $500, still is, and it turns out to be an excellent unit. There's 8 inputs, 8 mic inputs, and you don't need that, of course, but it's actually nice to have available channels, so you can have one pair set up for radiation, another for admittance. You know, it doesn't hurt. But the main thing about this was that it has digital gain. There are no knobs to turn, and it's not just that that's convenient, and it's easily checked right at the front panel what all the levels are, but that you can change the knobs. You can put both channels up a bit and nothing will change. I've just done one little test here, 2 admittance measurements. The red line is an increase in 2 dB in both channels, and you can't really see the red line. Chris Rogers has tested this unit or other ones, Octacaptures, and it really is very good that way. And that's a wonderful feeling to know that, for example, if you're pulling the microphone further and further away from the instrument, as I was doing in testing microphone distance, you can actually change both channels to increase the gain, and you're not going to screw up your measurements. So that's only one, I think, of 2 sound cards on the market that have digital gain, and they're both in that area of that price area. But I think that will be coming down into less expensive sound cards. And it's certainly, Chris has been looking into Raspberry Pis and things like that, which work entirely digitally. So I think that's probably going to be the way of the future. Something I never thought to see was inexpensive microphone calibrators are showing up on Amazon and other places. I don't know why, who buys them, but $85. I don't know how well it works. But Chris has got several inexpensive ones, and I've got a couple of calibrators now, and they're pretty good. But just the fact that they're making them shows that things are getting cheaper in areas I would never thought that would be addressed by mass manufacturing. So obstacles to repeatability. How hard you hit the instrument shouldn't really matter. You're dividing one signal by the other, so it's a ratio. So if you hit it twice as hard, it makes twice as much sound. You divide by one the other, you get a sort of a steady reading. But let's test it. I thought, let's get rid of the microphone. Let's do admittance. So I glued an accelerometer to the bridge, so there's no variables to do with the sound radiation and the room acoustics. And this is 20 taps with a PCB hammer, and this is going all the way up to 20 kilohertz. And this is with a metal on the bridge. I should say I flattened the pointed metal tip on the PCB hammer to sort of a almost flat lens shape. And this is tapping very lightly, but structural vibration measurements are to be envied. It's hard to do that well with radiation, but anyway, it just shows that the hammer and the tapping mechanism is working very well. Now, here I tapped as much, significantly harder, but still within the range. I wasn't clipping anything, and immediately things deteriorated, especially at low frequencies. And I have no idea why. I hope to understand better what's going on. And it doesn't really matter, but the more you understand about something, the better you can try and optimize it. So then I tried the same thing with radiation measurements. Now, Fan or Claudia, can one get rid of the panel at the top of your screen?
Which panel?
The one that has stop video security participants, because it always blocks my screen title.
You can put it at the bottom by.
Oh, hide video. Oh,
yeah.
Nope. No, that got rid of everybody else. Okay. Could somebody, Claudia, could you read what the title says?
Radiation repeatability, 10 light taps.
Okay, I'm back where it should be. Thanks. So this is tapping lightly 10 times. A little bit more than I did with admittance, but that general spirit. And you see right away that you don't have a lot of energy, especially at high frequencies. And if it's got to go through air and get to a microphone, the signal to noise deteriorates. So you get more issues. Now I hit it as loudly as I could without clipping. And funny enough, it got better at low frequencies where it got worse with admittance. I don't understand why. Everything has to do with the details of the impact and possible nonlinearities, but I would have thought they were the same with admittance and radiation. Anyone has any ideas, I'd be glad to know them. So in conclusion, variations in impact strength shouldn't matter, but they do. An automated hammer would help. So I made an automated hammer. I've been thinking about this for ages and different possible designs and tested a few. It turns out that it can be done really simply and inexpensively with a push solenoid. Basically, the solenoid hits a prong on the top of the hammer, it cocks it, it pulls back to its shell, and the hammer so that was very satisfying to sort of square away. And I did a bunch of tests in the last couple of days, and it's absolute joy not to have to get in the chamber and reach around instruments. And I think it's definitely the way of the future, or my future anyway. Oops. Okay. So this is the same thing. I did 10 sets of measurements for one microphone position, removed it from the rig and replaced between each. And now this is with the automatic hammer, and there is a few, peak heights of 1.2 dB changes, especially at high frequencies. But it's better. The manual hammer had several that were 2.5 dB or even more, and in terms of band averages, it's about a little better, a little bit worse there, a little better here. It's in the ballpark. It's not worse, which I'm very glad of. So the next thing, you have an automatic hammer, you could do it faster. The time window for the measurement is about a quarter of a second. So who doesn't want to do things faster? But it turns out that makes a difference. Here are I think this is again, I can't see the top of my screen. This is the quick impacts. Is that what it says?
Impact repeatability, 20 quick taps.
20 quick taps. Okay, thank you. And now this is 20 slow taps, meaning waiting about a second. And there's a definite difference. And in this case, I think I understand why. It's pretty obvious. The instrument needs to settle down between taps. Even though it's sitting on foam, the top end is held by rubber bands. So if you look at it, you can see motion. And if it's moving, then there's a possibility that the hammer is not going to impact the same place every time. It's worth it to be patient. So the next thing, the variations of the position of the rig operator. This is something Jim Woodhouse noticed right away a long time ago in Cambridge when I had some rigs over there, that moving around affected the measurement. And so here's 5 taps, just one microphone position, standing as still as possible. And then here's 5 taps, changing position between each. I mean, I was quite radically changing position just to see how bad it could make it. And yes, indeed, you should be careful about your position. And even I remember at Oberlin doing measurements, and people would be in the measurement room and they're not talking, but just the fact that they're moving around the rig, it does influence things. So the conclusion for that is stand still or operate remotely. And an automatic hammer does allow that possibility. The most obvious repeatability question is probably to do with the impact position or the mic position. The mic position is pretty easy to control. I'm not worried about that, but the tiny details of where the mic hits is much harder. And I think it is largely responsible for the repetition errors that we have had so far. But I don't have anything more to say about that now. I hope to have more down the line. Other obstacles, temperature and humidity of the measurement place. I was in touch with George Bissinger about this, and he said that he was working in an anechoic chamber, but just after a few hours, the temperature and humidity could go up significantly in there. And of course, well, that changes the sound transmission and air somewhat, but it also can change the instrument a fair bit. All of which to say, if you're doing repeatability things, do them as close together in time as possible. On the other hand, there's the variability of the instrument itself, which is sometimes, I think, confused with the measurement process. Instruments are changing all the time. So what does it mean to take an individual measurement? It's a kind of, you never measure the same violin twice philosophy. But in order to know that an instrument's changing, you've got to be confident that your rig isn't. So what I'm trying to do is understand it as well as possible, the uncertainty that comes out of the measurement process. So then it would then be possible to measure how violins change over time. The experiment I've long wanted to do is, it might be possible when there's more hammers around, is to string up an instrument that's new with steel strings so it doesn't lose too much tension, and leave it in the same place in an enclosed thing and just measure it every day for a year. And let's see what happens. I don't think anyone knows the answer to that. And it would be interesting. And then try changing humidity. There's so many things to learn about instruments and how to measure them and how they change over time. So let's just look more closely at what happens when the hammer hits the bridge. Here's a little thing I did some time back on the effect of the tip hardness. So the PCB metal tip, I just tapped a massive metal block, so we weren't dealing with anything complicated on the receiving end of these blows. And the PCB metal tip were good all the way up to 20 kilohertz and beyond. I made a custom tip out of the stuff they make cutting boards out of, high molecular density polyethylene, something like that. And that's the middle one. And so how are we rating this? We're seeing how much energy is in each blow across the frequency range. There's a rule of thumb I learned somewhere that we want to keep it, we don't want it to drop more than 20 dB. So I put this sort of red zone down here. The metal tip never hits it. The custom polymer one, which is probably then softer by a fair bit than Claudia's plexiglass tip, hits it around 8 kilohertz, but it still works fine, or 7 kilohertz. The PCB soft tip is a real disaster, though. if you're trying to do radiation measurements. It's softer than it needs to be. It goes below at about 1.5 kilohertz. It's also tricky. When I got one, it was doing all sorts of nonlinear measurements. And it turned out that the tip was too long for the hammer. So there's a little air bubble there. And I talked to the guy who designed the thing, and he acknowledged, yes, that was a problem. Well, why don't we fix it? But apparently you should clip your tip with a fingernail clipper or something like that. So if you are using it, do be careful. In the end, I think I use a flattened metal. I don't do it too hard, and I don't really care whether I put a little dent in my own bridges. If I was measuring more expensive instruments, I'd have a bit of a more safety margin. Well, I could do a lot of things, like just stick on a tiny layer of bridge parchment, something like that, or it's easy to get softer. But on the other hand, why don't we design our bridges to make them easier to measure? For me, that's a reasonable question. I think it was some early researcher who said that the violin isn't designed for the convenience of measurements. Well, I think it should be, and as the violin culture absorbs more and more measurements, which it surely will, then why don't we inlay a little bit of hard stuff at the corner of the bridge in the center of the top? I mean, people do it under the E string. There's absolutely no reason why not. There's all sorts of things you could do to make the measurements more repeatable. That way you have a specifically designed spot where you hit. George Stepani, I think, put tiny little bits of titanium, stuck it to the side of the bridge, and that solved the hardness problem. It's not good enough just to have a hard hammer tip if you're hitting a relatively soft wood. You'll reach the limits of what the wood can do. But realistically, we're not usually concerned with sounds above 8, 10 kilohertz because the violin doesn't emit them with any strength. So the ideal impact, oh, I seem to have lost no, that's right. So what is an ideal impact? An ideal impact would be infinitely short pulse, and its spectrum would be completely flat. That's what the physics of it is. What does infinitely short mean? Well, if you're sampling at 48 kilohertz, and if it's less than 1/48,000th of a second, then effectively you don't have to worry about the frequency dependence of it, only how hard you hit. But in reality, here's what the PCB hammer did on a typical impact. And what you see is it's staying above the 20 dB floor, but you have these oscillations in the spectrum, and these are caused by more than one bounce. So here's the initial impact, then it seems to hit it again, and then it sneaks back and hits it again. The initial impulse is very short, a tenth of a millisecond. So what's going on? Thankfully, Chris Rogers did a slow motion video. So I'm going to play this. It's going to hit the hammer, and then I have it edited so that it loops so we can see it a few times. So first thing is just watch the hammer as it hits and watch the bridge. Just keep your eyes there. Then maybe on subsequent ones, sort of follow what's happening up and down the hammer shaft. See how the bridge moves over? And if you watch it, you can see that it bounces back and hits the hammer there. Focus on that this time. And the next thing to see is how the bending waves goes up the shaft, down again, and sort of nudges the hammer slightly up and down. So I think that the three little hills that we see, the three little the three-part nature of these impacts has to do with just those three things, so that by changing the arm design, I think you can tweak that. But the reaction of the bridge, you're not going to change. So let's go. If this is the PCB hammer, here's what happens if you put a heavier, I've been building hammers out of spruce. This is actually well, there's a number of advantages. You can get rid of wobble from side to side. And it's potentially very light. This one is relatively heavy, 3.3 grams compared with the PCB arm, which is about half of that. And it's got this metal connector, which PCB forces you to use. So it's relatively heavy, but still, you can see that the those three things have come much closer together, and we don't have those little oscillations. What we have is a loss around 2 kilohertz, and it goes back up. And it turns out that this shape seems characteristic. Here is a 5-gram hammer, and we see that now at 2 kilohertz, it goes quite low, then comes back up. And again, these three are together. So why do we want a light hammer? I think somebody asked. The heavier the hammer, the more slowly it's going to rebound. The longer the contact time, the quicker the frequency fall off will be. So if you want to measure high frequencies, you want a very short impulse, very short contact time. So ideally, you would have a very light something. I mean, we're brainstorming the other day in the shop. What if you had tiny ceramic balls you were shooting at high velocity at it? Something like that. They'd hit, they'd bounce off very quickly and be gone. That's sort of one way of thinking about an ideal impact. In the real world, we deal with actual arms. So this is the one 3.3 grams that's on the solenoid-driven hammer, and it's pretty respectable. It certainly does fine, but I haven't really gotten into optimizing the arm, and it can be made considerably lighter. And with Tom's even lighter hammer, I think we can have a pretty impressive force spectrum. Okay, so I conclude that many hammer arm designs are fine. The PCB arm says it's modally tuned, and that sounds impressive, and I'm not sure what it's tuned for or at. I think it was probably made to be good for holding in your hand and tapping things with. But it's not very good to my mind for rigs because it can rotate inadvertently, and the way the hammer is screwed on, it can come loose and turn. There's a lot of things that go wrong with hammers every so often that you can get rid of with a different arm design. And I'm no longer worried about particulars of materials or longer, shorter. It could be made to work in a lot of ways. So the thing is to find the most stable, rugged, usable one and stick with it. So let's talk about measurement space, because that's always the biggest threat to radiation measurements. And Gabi was, when he started, he had an anechoic chamber. George Bissinger has an anechoic chamber. It's sort of the golden place to do measurements, but you can't, unfortunately, lug one along to a artist's hotel room. But let's just think a little about anechoic chambers and what they are. So an anechoic chamber has two distinct jobs usually. One is to keep sound out, so sounds from the environment from getting into the measurement. So what they rely on is usually very heavy outer walls, often poured concrete or multiple layers for these places where they're trying to measure the sound of a single raindrop falling. You know, it's enormously expensive. And the other thing that they're supposed to do is absorb all reflection inside, which means having sound absorbing panels. Now, there's a number of ways that can work, but the usual sort of porous foam depends on particle velocity, air particle velocity. So the air's got to be moving for it to do its work. Now, right at the wall, it's going to be zero, and it's going to reach, the particle velocity is going to reach its maximum for any given frequency at, well, the first maximum will be at a quarter of a wavelength. So if you think for 200 hertz is maybe the lower limit for violin sound output, that's almost a half a meter. So suddenly we've got thick walls plus half a meter distance to get to our absorbing material, or absorbent material that's half a meter thick. We can see those panels are expensive, especially if you're getting the professional foam. And all of this makes building an isotope apparently hopeless. Also, the internal dimensions have to be suitable for it to have a, an even response across the frequency range. A small room will have, right in your measurement frequencies, big humps in the response. That's true for listening rooms. Ideally, we want a large room that's pretty dead. So a traditional chamber would have heavy walls, a bunch of thick absorbent material, and a fairly large internal volume. None of which are available in the workshop. However, well, let me just, before I get to the however, this is a measurement we made years back in Jim Woodhouse's office at Cambridge and in their anechoic chamber. And this was encouraging for me because the blue was made in his office and the red was made in the chamber. And granted, there's some reflected sounds that are amplifying things. We have the same basic shape, which said that it's recognizable as that instrument. And of course, Jim Woodhouse's office is presumably optimized for analyzing measurements, not for doing them. So in any given space, we can probably do better than that. So I've evolved over the years. It's in all sorts of hanging up curtains and sticking things to the wall and generally treating the room. And finally, a few years ago, expanded it into a full-fledged, I won't call it a chamber, it's more of a space. Now, it works on an idea that came to me. It's probably not a new idea, but it's what I came up with. What if you're not worried about keeping external sound out, then don't put walls on your chamber. Don't put a rigid barrier around it. So what we have here is about a 6 by 6 by something, or 4 by 6 internal space. And then these porous walls that absorb a lot of the sound. And then it bounces around your room and gets diffused and gets absorbed somewhat. And then it has to get back into the chamber. So the inside the chamber has the very high modal density of the room. This room happens to be about, I don't know, 24 by 30 feet with an 18-foot ceiling. So it's big and it's fairly live, but it means I don't have to worry about big humps in the low frequencies. So it's only a matter of how well it's absorbing. And when I made it, it seemed very good. You go inside and it seems quiet and dead and like a terrible place to play violins, and it seemed to give good measurements. So I thought it was time to actually test it. And I'm not a professional acoustician, but I understand that they burst balloons. A balloon will give a quick quick bang. You can also use starter pistols and things. And so I burst the balloon, or a few balloons, and inside the chamber, and this is the impulse that it generated, the waveform. Now, balloon doesn't make a single impulse the way, let's say, a wire break might. It's actually, you can see slow motion films of them bursting, and what happens is the wave comes out and it collapses back in and various things happen. So this doesn't mean it's bouncing around my chamber at all. The entire length of it is, we call that, this is 20 milliseconds. And it's good and dead by the end of that. And consider that the impulse response for violin with string damps is about 200 milliseconds, so we're about a tenth of that. So that seems promising. But again, I don't know how they really rate these. I burst the balloon in the chamber and put a matched pair of mics, one inside and one out. And here you can see the outside one, the room reverberation. And I had to change the gain on the microphone. So I would say there's an attenuation through the workshop, through the chamber walls of something around 20 dB perhaps. But then remember, when you're working, it's going to go out and lose 20 dB and lose another 20 dB on the way in. Oh, and this was a balloon burst outside the chamber, and then measuring inside the chamber and measuring out. In this case, there's a 20 dB difference in gain, and they're normalized to the same level. So we can say the chamber wall attenuation is indeed about 20 dB. I should say that the wall itself has about 4 inches of Sonex foam and then there's about 8 inches of absorbent panel like mineral fiber, or I'll talk a bit about that in a minute. And then some cheap acoustic foam on the outside. But from all I've learned, I don't think the Sonex panel, the expensive part, is really that important. Oh yeah, this was fun. I found that there was online a balloon burst in the chamber at Salford University in Manchester, UK, and they advertise their services for doing acoustical testing. And it's a big chamber with a really, really low noise floor. But their balloon burst, again, I don't know how to compare really. They use a different brand of balloon than I did. But oops, you know, I was pretty pleased by all this. Now, later on, I'll show some strange things that happen measuring inside my chamber. I don't know whether they're because of the chamber or because of the near field properties of the violin. But let's say that this kind of what Evan calls a flow resistant shell inside a room is a good model for an anechoic chamber. Then how small could it be? Well, without going into it, I thought I threw together a design which Lonnie rendered for one that was sort of modular. You could take apart. You could, for example, use it at Oberlin. It's the internal volume is 4 feet by 4 feet by 2 feet, and the operator would never get into it. You'd open the door and your rig would slide out. And you'd need an automatic hammer and an automatic way of rotation. But that's just down the line a little. So I would actually love to test this maybe as a new Oberlin project. And especially if someone wants to have one for their shop, you could put it on casters and sort of wheel it out of the way. Now, Roxol is a brand of mineral wool panels, and they're, I think, the cheapest of all the sort of thing. They're about $35 each for a 2 foot by 4 foot by 4 foot. So you could actually, including the cost of wood and everything else, do a chamber like this for something like $900 with a bit of labor, which is pretty darn good compared with, you know, the sheer impossibility of a real anechoic chamber. But how well does it work, and what are the limitations? I'll report further on down the line. Okay, so a big question: how many microphone positions and where should they be? There's really not a lot of measurements out there other than George Bissinger's, like spherical measurements. George Bissinger used 266 microphone positions around a sphere, microphone distance of 1.2 meters. And he did these measurements for a lot of instruments, including the 3D Strad project, the best known ones, but also he did 6 violins made by David Rubio for Jim Woodhouse. And Jim was kind enough to dust off these and help me translate them and look at them. And he also made this wonderful movie of the radiation as it changes with frequency. Now, what are we seeing here? This is radiation. The further it is from the center, you know, the more energy there is. And this is the front of the violin. This is the back of the violin. And this is the frequency. So this is down at 250, a little below A0. And this is gonna, when I start this movie, it's gonna start moving up all the way up to 4,000. And so watch what happens. So 500 hertz. We're coming up to kilohertz. Now we're coming up on the bridge hill pretty soon. See how it's mainly coming out of the front now? A lot could be said about that, but the alarming question for someone trying to measure violins is, where on earth would you put a microphone to capture all of that? Or it's obviously violin sound radiation is very complex and very frequency dependent. And the idea of using a single microphone to give a definitive, to capture it definitively is just absurd. Now, the question becomes, what's the smallest number you need to get a reasonable estimate of that? But that's one question. So, oops. So this screen, this shot shows the red line, which is just Jim took out of the sphere the equatorial positions, which is kind of what we're measuring with my rig. So if you're, imagine pointing at the bridge and then going around the violin, that's what the red line represents, whereas the black line represents the whole spherical radiation. It's been smoothed a little bit, but it's not bad. I was delighted to see this. I was expecting a real debacle, and it's pretty good at low frequencies, which you'd expect, but higher up, it's not bad at all. So let me. This is an average for all six. Let's just look quickly at all six of the violins to see what the range is. If it varies a lot from instrument to instrument, which would be important to know. But what these little circles up here, this just means that the two are about equal. This means that the red one's higher. This means the black one's higher. So I'm just going to leave those same ones there, but see how it changes from instrument to instrument. So instrument number 1, it's indeed that pattern. And again, now this is closed up here. This is the largest gap of all of the instruments. That's only maybe 1.5 decibels. Okay, so my conclusion from this is equatorial readings seem to be a good approximation of spherical, especially at low frequencies. And in terms of band averages, the equatorial seems to overestimate the transition hill by something under a decibel, 0.8. And it underestimates the high frequencies by about 0.7. I'd want to test this with more instruments in different conditions, but it gives a good and reassuring sense. There's a couple of buts that should be said. This was 24 microphones around. If you use 12, how much are you losing? That's an easy one to test. I don't have that test here, but it changes a little bit in the high frequencies, but it seems like 30 degrees as a angular increment is just fine. You can always do more around if you're worried about a particular instrument. Another, I was supposed to say something. Oh yeah, another thing that's another but about this is what Jim did was took each microphone position, which is each point here, and did a RMS average of all of them to get the curves that I showed above. Now that gives equal weight to every microphone. In fact, the sort of the area density of microphones up here is much greater because George Bissinger used an array evenly spaced along an arc, which rotated around the instrument or vice versa. So you've got more density of reading here, which means to get an actual reading, one would have to diminish the importance of each of these by an amount equal to the area of these quadrangles, something like that. And also, I think it explains this dimple here. I don't think that's real. I think that's because there's one microphone at the end only. But I hoping that Chris Rogers can help me putting in some compensation for this so that we can make these, just double check on the final results. So making sense of microphone difference. This isn't saying anything about measurements. It's just some of the different distances. The player's ear is about 15 centimeters, depends on the player. Their stand partner's ear might be half a meter. Microphones for recordings are often about a meter away. The wavelength of A0 is about 1.25 meters. So all of those are in the near field, at least for the lowest frequencies. Measurement positions that were used, Dunwald in his famous experiment had his a meter away, I think, in an echo chamber. George Bissinger, 1.2 meters. Martin Schlesky in his workshop went down to 50. Whenever you're in a sort of a liver environment in an echo chamber, you want to get as close as possible in order to reduce the amount of room noise compared with direct sound from the instrument. Now, there's trade-offs in doing that we're going to talk about. I started at 50, went down to 37, and eventually took it down to 20 because I couldn't see any difference in the shape, or not much. And it really helped with being able to do measurements in poor conditions. So I'm still at 20, and I'm not sure I'm going to change in spite of everything that is to come here. So just the wavelengths, open G is about 1.7. And if you're talking about the various high frequencies of the violin, maybe 4 centimeters. So that's just to get a sense of the distance we're talking about for a full wavelength. Now, the first thing acousticians talk about when they're talking about radiation is near field and far field. And I would love to get Evan Davis to do a talk about all this. Maybe we can book one right after this because he's a real expert in these things. In the meantime, I'm poking around various sources to get explanations. This nice diagram was by C.E. Piquet's, I don't know if I'm pronouncing it right, about the acoustic radiation of organ pipes. And if you imagine this is the end of an organ pipe, he's treating it as a piston. So you have this about a half wavelength here where he calls it the circulating near field because energy is sloshing back and forth as it does near the surface of the violin without going anywhere. And that has to happen for an organ or you wouldn't, the pipe wouldn't work. And then up to about a wavelength or wavelength and a half, he calls it, it's circulating and propagating. And then there's this transition zone. And he puts 2 wavelengths to infinity as the far field. And everyone acknowledges these are approximations and there's of course a smooth transition. But the main thing is that the kind of, what's I think known as the evanescent waves that circulate here, they don't get far. They diminish much more quickly than the other waves. So you start getting a little bit away and they're not nearly such a problem. But the question is, this is for acoustically small sources. A violin is acoustically small, kind of compared with its lowest frequencies, but not compared with its high. So I also found, just trying to learn about near field, far field, a lot of the work on that is done with radio frequencies. And I found this great formula for radio antenna measurements, and they calls it the reactive near field. I like that. And there's a circulating one. Reactive because things that happen in this range can change the instrument itself, the behavior, or the antenna in this case. If you have, well, let me not say about anything more about that, except to say that this turns out to be the wavelength times divided by 2 pi, which is like 0.159 times the wavelength. And that's much shorter. And then I found just the other day in Colin Goff's musical acoustics chapter of the Springer handbook, the same formula written another way, saying the near field was basically that formula. And now, obviously, this is a simplified way of looking. I'm not trying to pin any interpretation to any of these people who wrote this. It's just me trying to get a sense of what we're looking at and translate that and what it means for measuring violins. So if the near field extended half a wavelength, as the Piquet says, then we see that for A0, it'd be about 63 centimeters. For B1, about 40. For B1 plus, 33. Here I have my mic at 20 centimeters. It's well within the near field of all of these. So this is C4 at 25. And then if it's indeed this smaller number, suddenly everything changes. I have the mic really outside of all of the reactive near fields because A0 is 20 centimeters. And I like to think that I stopped my mic there because of this. And indeed, when I went further, funny things started happening. So in a sense, that's true, but that this is a formula that, or a definition of the near field, or the near field that would be encouraging for me. Is that, does that make it correct? We have to measure to find out. So this was a measurement I did a while back, simply moving the microphone from 55 centimeters, to 15. And when I say these distances, I mean from the rotational axis, the axis about which the violin is rotating. So it's essentially the center of the violin. And that would be about 15 millimeters below the surface of the top. So 15 centimeters in this case is about 10 centimeters from the top of the violin, and not very far from the ribs when you turn it in that orientation. So at any rate, though, this was not discouraging. You see kind of the same shape. As you get closer, the amplitude goes up, so it sort of spreads out nicely. There's some things where it doesn't correspond very well here, and some interesting things here, but it's not a disaster. So I decided to do a more careful measurement, and this is starting with it at 10 centimeters and moving it in 5 centimeter increments all the way out to 1 meter in my chamber. And the first thing you notice, there's a lot going on here that to me is actually quite puzzling. And then it kind of settles here, but we wouldn't want to say that microphone distance doesn't matter. It does matter even in an anechoic chamber. This is with half a centimeter smoothing. And again, it's just one microphone position, moving the microphone out incrementally. And let's look at the individual. So this is at 10 centimeters. I'm just going to scroll through these sides and just sort of watch the changing patterns, especially around the A0, B1 minus. So 10 centimeters, 15, you see that dropping, A0 is dropping. 20, which is what I do, and that's a very familiar balance for me. 25, okay, it's not changing so much. 30, it's not changing so much. 35, but look what's happening. B1 plus is creeping up. So go back. It seems to stabilize. Now the balance between B1 plus and B1 minus is going crazy. And now it's rebalancing itself a little. But whoa, what's happening now? Again, it shifts dramatically. And at 85, we've got this very bizarre looking balance to my eye. And this was very disheartening to me. Does that mean I've been looking at this wrong all the time? And there aren't references one can't go to literature and find what a microarray full full measurement looks like as an FRF. They simply aren't around. So what if it looks like that? But then just as we're getting close to a meter, it started rebalancing itself. And we're not yet out of the near field by the we're not yet up to a full wavelength of A0, but it's as far as I could go in my anechoic chamber. So I really need to retest in a larger chamber, or as Jim suggested this morning, just take the measurement outside and try it there on a quiet evening. So I will report more on this down the line. Another possibility, though, is that my chamber is too small. Okay, so, but if you just stand back a bit, it's not a disaster. You know, things are within 2 dB mostly. So, question, this was just a single microphone position. Now, with a violin, the acoustic centers of the modes aren't in the same place. A0, it's slightly outside of the instrument. I mean, it shifts around. So when you're measuring, as you turn a violin around, you see A0 go up and down wildly because you're moving quite far. I'm not putting this very well. Well, let me just ask the question I'm asking here. Would a full rotation cycle smooth out the discrepancies we saw here? So I did that, and this is just for 5 positions, 20, 40, 60, 80, and 100. And so the answer is a partial yes. We see a much more agreement now up here. I mean, we're talking about plus or minus half a decibel. Remember that, you know, just the repeatability isn't that much better than that. But still, there's definitely things going on around here. But another thing came to my mind. Because of the size of my chamber, the violin is quite close to the walls. And I realized, well, of course, if a violin is in the reactive near field, then the walls are influencing its behavior. So imagine the violin in sitting in infinite space, and there's this acoustic panel. It's like a black hole, and it gradually floats along. It's not doing anything, but then if it gets close enough that it's absorbing some of the energy that should be recirculating back into the violin, then we're changing the behavior. We're changing, in a sense, the radiation behavior of the violin. So it would make sense to do the same measurement with the violin in the middle of the chamber. I couldn't get as far away. I can only get maybe half a meter. But if that clears up some of the anomalies, that'll be very interesting. Or it may be simply the case that we have to make allowances at low frequencies for, you know, absolute spectral balance when working in the near field. So questions I didn't get to were, how do you compare measurements inside and outside of the chamber, except for that brief old one I did at Jim Woodhouse's. I haven't explored that further. And how does radiation compare to admittance and internal mic measurements? But I think I've been talking for a long time. So just a few things about the near future, hopefully. This is Chris Rogers' first working model of using a Raspberry Pi, this tiny little computer. They're inexpensive, I think 50, 60, 70 bucks. And that's everything's on there, but you know, the software, the in and out. And so it could be possible to stack a number of these and then use multiple microphones, which would be a big time saver. My dream would be to walk over, put an instrument in, hit it once vertically, hit it once horizontally, get the answer and walk away. And I think we can get there. For example, what came to my mind first is you buy a hula hoop and you get a bunch of lavalier microphones and you mount it around it. All it needs from there is multiple channel processing, which will be available. And then you have to think about microphone calibration. But you know, that's doable, but I think that's a very promising area. I'm excited to work on that with Chris. So that's all I have to say. I will throw it open to stunned silence or to questions.
Thank you, Joseph. Are there questions? Remember to use the raise hand.
But I can't raise my hand. Can I start?
Yes.
Yeah, thanks, Joseph, for this talk. There is something that you didn't really address is the direction, the angle with which the hammer hits the bridge. And in particular, when the bridge is like this, how do you manage to hit it properly horizontally? Because basically only one part of the tip of the hammer will hit the bridge. So if you know, because you said that, oh, the violin hasn't been designed to be conveniently measured. And indeed, the bridge with this angle like this, when you hit it, and I felt that this is a really one of the main problem I have to remove the double bounce and to hit it with the right angle.
I agree. I didn't specify. I use that corner as the point to hit, and if the hammerhead is flat, then it defines it reasonably well, but it's not ideal. I agree.
Because you will have an angle between the flat surface of the hammer and the bridge, which is not.
No, but you hit at the point, at the corner. So I don't know whether you can see my hands, but the bridge comes and then there's a corner, and if you hit at the corner, you have a defined line.
Yeah, but
it gets left defined the more times you hit it.
yeah.
But that's okay. I think that it's a source of uncertainty. I completely agree. It's workable, but I really think that I'm going to design a bridge which has a little measurement point there and in the center. Why not?
Yeah, and I had another thing about, because you asked for hints about why your measurements with the accelerometer are much more different than with the microphone. And I was really puzzled because it was really below 200 or like around 200, 300. And that's a massive difference. And because you don't see this in the microphone position, that means it's not due to the hammer, but due to the accelerometer. And I remember having done some measurement with Jim, and I had problems like this. And then Jim told me that it's not because of non-linearity in the system by itself, it's non-linearity between where you actually, how you attach the accelerometer to the bridge. And so when you hit too hard, the accelerometer, even if you try to glue it, especially I was probably not gluing it with super glue at that time, and then it was actually, the accelerometer could actually bounce back because of the strong impact, and that was causing problems. So the non-linearity was the contact between the accelerometer and the bridge, with the accelerometer not being fixed properly. And
that may be it. At the same time, the accelerometer in that experiment was really glued on very thoroughly.
okay.
And I might expect at high frequencies, it would start to have an extra degree of freedom, but I think at the low frequencies, it couldn't have moved. I may be wrong, but
did you check the coherence of the measurement when you were hitting hard? Was the difference between different?
Oh yes, the coherence dropped. Absolutely, yes.
Okay.
This is something real, and
so even if you control for example, you just say, okay, I will hit hard, but always from the same distance. This will give coherence. Yes.
Can I feed in a comment here?
Yeah.
Yes, please.
The plot you were showing that had that low frequency anomaly, that had been turned into admittance, yes?
Yes.
So therefore the accelerometer had been integrated. And I suspect that's where your noise has come from.
Mm-hmm.
The accelerometer has got lousy signal at low frequency, and then you've boosted it by the process of integration. And so you've boosted the errors by the process of integrating, I suspect.
That's interesting.
It's a factor of, you've multiplied it by a factor of, you've divided it by the frequency, essentially, in integrating. So as your frequency goes towards zero, you're dividing by nothing. And so the errors are getting boosted by a factor proportional to frequency, inversely proportional to frequency. Yeah.
Well, I have to think that through, and
offline we can talk about that, but I suspect that's the issue.
Brilliant. Thank you.
Okay, Jesus Torres.
Thank you. Hi, Joseph. Can you
Hi.
hear? Okay. With all of these considerations of the impact in the bridge, the classical setup of Eric Johnson is horizontal, and you have a vertical position your violin.
Yes.
Tom, for example, has the violin in his lab horizontal. So we can compare these admittance measurements, horizontal and vertical.
Yes.
Yes, no problem, because you are hitting the bridge here in this way.
Yes.
In this way, and you are not moving the hammer.
Oh, I'm sorry, I didn't show a diagram of. So for the horizontal, I hit the side of the bridge as Jim showed for admittance, or very standard. For vertical, I go straight down at this highest point of the bridge, so a little closer to the D string than the A. So with all of these, there's a presumption that the bridge is rigid enough up there that it's not, you can see the forces moving in a straight line. So I think the idea is to strike at two normal directions. You could, for example, strike at 45 degrees to a little prong in the center of the top. Imagine a little ceramic ball bearing there. It's one way I think about doing it, and taking two measurements at 45, then you're tapping both at the same point. So in a sense, it would be better defined. But I haven't done a lot of vertical admittance. I haven't done a lot of admittance in general. I did, if there was more time, I would have talked about the difference between admittance and radiation that I see in terms of where the peaks are. For example, the bridge hill shows up at lower frequencies in radiation than admittance. In admittance, it tends to peak about 2.5. With radiations, typically 2 or below. But that surely has everything to do with radiation efficiency. Anyway, it's a very interesting area that I don't think has been explored much. But did I answer your question? I'm not sure.
Yeah, that's fine. Thank you.
Joseph, I'm just wondering whether Reza's question was not about the fact that what you say about horizontal is not what Jim considers as horizontal, because Jim is always going tangentially to the bridge, while your horizontal is not. So if you have the bridge, you are hitting like this, while Jim tries to always to hit like this. So it's tangential to the bridge.
Yes, I understand. And there's some advantages to do that, mainly as you hit a flat surface. But then to get something at 90 degrees, I'd have to be doing vertical at an angle, which makes me a bit queasy. I think that you just need to get, if you're dedicated to getting, the two measurements, pick your two, and I think the software can sort the rest of it out, as I understand it. But isn't Jim interested in something he calls rotational admittance? And I'm not. Maybe Jim, could you pipe in here?
That's a different thing. If you're measuring admittance in order to couple it to a bowed string model, then you want to be in the direction of bowing. If you're measuring it to characterize instruments, as you are, to compare one thing with another, anything you do is fine as long as it's always the same. So it doesn't much matter. The only thing you said that was not quite right is that you can choose any two directions and the software will sort it out. That's only true if you, okay, it's okay for microphone measurements, you're right. For admittance, you have to measure the cross term as well, because you need to rotate your accelerometer in two directions or your laser, and you need to remember to do the cross one as well as the two driving point ones. You need a little matrix, and then the software can sort it out. And
with radiation, of course, you can't do that.
No, for radiation, it's perfectly true. Any two directions at right angles will do. And you can combine them in software.
And is that the case that you just add the complex in phase and out of phase to get
something to do with
something like that?
Yeah, it's straightforward, really. Yes, you just resolve the direction you want as a sum of the two directions you've got. So you could do that for two directions at right angles at the same point. The only minor difficulty with yours from that point of view, it would be better to be on the corner of the bridge and then perpendicularly on the same corner rather than in the
No.
middle, but
Well,
it depends what you want to know.
No, I would put a little thing right at top center of the bridge, like a little
And do both ways,
little
yeah,
bead, and then I could hit it from any angle.
from all angles. No, we once did that. In fact, when I first visited George Bissingham, I carved a bridge for his wife's cello with a little block left sticking up in the middle out of the original wood, so we could do the full matrix of things. Some years later, it came up on Toby, for those of you who know about that, the online discussion group, people saying, has anyone seen a bridge like this before? And Wendy Bissinger had sold the cello with that bridge on it and caused major puzzlement.
All right, John Soloninka is next.
Hi, Joe. Great discussion as always. A little off topic here. When I as a player, I often hear violins that as you're playing and going up the scale, suddenly the radiation goes from left to right or far away towards you. And as I was watching I don't know if you have time to play it again, but as you were looking at that sequence of the radiation of the instrument, there was a real flip one time around 600 hertz. And some of the discussion people have been saying that was like B1 minus to B1 plus or something. Do you know what that is? And do you know roughly what frequency that is?
Would people be interested in seeing that again? I could try and find it. Fan, is there, do you think it'll take?
Yeah, I mean, yeah, why did you go find it? Yeah, let's see.
Can I answer that one while you're looking?
Yes.
First of all, the video I think is on my website, so you can watch it again anytime you like on that euphonics.org. What I think that flip is, I put this in the chat, but it goes back to a paper of John Schelling's from the 1960s. Remember, these are all being driven at the bridge with the same hammer blow for the different microphones. The frames of the video are auto-scaled, I think. I'd have to remember exactly how I did this. But the flip, which will come up in a bit, is the polarity reverses. The polarity of the monopole component driven at the bridge flips at one stage. So there's a frequency where it's going from plus to minus, so it goes through zero in between. And so you suddenly get a little narrow frequency band where there's only the dipole left because the monopole component has gone to zero.
We just saw that.
Okay. So it's not so much a flip as something disappearing while it changes sign and coming back in. Basically, A naught has the volume change in an antiphase with the bridge, whereas by the time you get up to the B's, they're in phase. Somewhere in between those two, there's a polarity shift.
I can't go frame by frame here.
Yeah, looks like about 500 hertz. Looks like about 500 hertz. Yeah. That's very interesting. I gotta go try that. I gotta go try and see if I can physically hear the change in radiation. Anyway, thank you for that.
Good to see you.
All right. Next is Hans Johansson.
Oh, hi. Can you hear me?
Yes.
Hey, Hans.
Hi, Joe. Thanks a lot for that. Actually, your talk was so good that it actually annulled all my questions. Answered most of them. So
that is a true compliment.
Yeah, I do have a couple of little questions. I noticed that on your PCB hammer, there's a flat.
Yes.
Did you file it off?
Yes, I talked to the people at PCB first. Was I going to ruin anything? Only my warranty, but
yeah.
But no, yeah, it's just titanium you're going through at that point. You don't hit the sensor.
Right. So I thought about doing that, but I never had the guts. Anyway, another thing is the accelerometer on the picture, which is glued to the bridge.
Yes.
Can you explain that?
How do you mean in plane?
Well, I mean, it seems to be glued onto the flat surface of the bridge, not on the end.
Yes, but I glued the side of the accelerometer.
Ah, okay. All right.
So actually, I pre-glued the accelerometer onto a little spruce base. So it means you could stick it on and move it around, rotate it without that problem you're alluding to.
Okay. Just one more little question. The comparison with the Rubio instruments, were they, root means, are they RMS averages? Do you know what I'm talking about?
Yes, they are. Jim, am I right there?
Yeah, well, you are RMS is what you asked for that particular thing. We looked at linear RMS and magnitude averages. I think they're equally easy to do.
All right.
Okay.
That's all. Thanks a lot, Joe.
Good to see you. Thank you.
All right, Joseph Najivari.
Can you hear me?
Yes, I can. Go ahead, Joseph.
My question is rather theoretical. I direct it to Joseph, but also to other theoreticians. You apply the impulse with your impact hammer at the bridge. And I wonder how much information we lose by ignoring the impulse at the other end of the string, like at the knot. Have you tried to hammer, to apply everything what you have with the rig, the impulse at the ebony on the knot?
I'm sorry. Have I tried tapping the nut?
The other end of the string.
Oh,
the Helmholtz motion runs back and forth.
Yes.
Between the bridge and the other end. So I wonder what the result would be if you hammered the ebony, the hardwood, which passes the vibrations very efficiently into the body, that we know by touching a tuning fork at the site. You will hear the same loud sound what you hear when you touch the tuning fork to the bridge. So it's a legitimate question. Would it be worthwhile trying to get a response curve at the knot side of the fingerboard?
It's a perfectly reasonable thing to do. In fact, people who do modal analysis probably do that all the time. I'm not a theoretician, so I can't address it at that level, but just instinctively, if you hit the violin anywhere, it'll make a noise. Therefore, there is a radiativity associated with each spot, and you could measure it. I think you're interested because you had some ideas about the sound. Well,
Joseph, well, actually both Josephs. The only practical thing I would point out in terms of the response at the nut is the overwhelming majority of the time we're not playing with open strings. So the string is not vibrating at the nut.
The other thing to add to that is that the bowed string mainly vibrates in the plane of bowing. So the force of the nut is parallel to the fingerboard, not normal to the fingerboard. So it's not tapping normal to the nut that you would want to do. You'd be needing to apply a force tangential to the nut.
But you could hammer the knot in any direction to see the difference.
No, at the nut you could do it. It's easier to do that test with the wire brake method rather than with the hammer. It's been published, this, hasn't it? I mean, certainly for guitars, it's cleaner with a fretted instrument to do these measurements at the different frets. It's an issue for electric guitars because if they want long sustain, they fuss a lot about making the body really solid, but they still have a thin, flimsy neck, and they can end up with something where the string loses more energy into the neck than it does into the body. In the violin, I forget the numbers, but it's sort of 20 or 30 dBs lower at the low frequencies. You know, there's not all that much energy that goes in, I think, at the nut end, if I'm remembering right. It's in the literature somewhere.
Can I comment, even though I'm not?
There's somebody who's talking, but who's very...
Is it Colin?
Colin, yes. But very faint.
Colin, you're very faint.
Sorry, I don't know.
Far away.
Colin, you need to somehow fix your, I don't know, microphone or something in your computer because you're very, very faint.
I think he left his microphone inside the violin. Internal cavity measurement.
forget it for the moment. Okay. Go to someone else.
Do you want to
Oh,
do your question, Colin?
Well, if you can hear me, I mean, I have done measurements, in fact, on hitting at the neck, and it quite obviously depends on frequency, and it is quite an appreciable effect when you get to higher frequencies. As you can hear, if you hit the violin, you can hear the different sounds from hitting the violin at the bridge or hitting it at the nut end on the neck. That's all I want to say.
did somebody understand that?
Yeah.
Yeah,
Yeah, we could hear that all right.
I didn't. Could you repeat briefly what he said?
Well, perhaps, yes. I mean,
It's more of an effect at high frequencies than low.
but it's very appreciable. I mean, it's only about 10 dB, 20 dB down, even at low frequencies. And you can hear that immediately when you hit it. I mean, I think in all these things you have to ask you why you're doing it. And whether you're doing it from being a research paper or something that's going to be helpful for the maker. And for the maker, I think some of these things are not very important for them when they're trying to adjust an instrument. In any case, Jim, it was a fantastic talk. And also Joseph. And I have enjoyed everything I've heard. And I'm very impressed with everyone who's done. And my best wishes to everyone.
Thank you. Great to see you, Colin.
Thank you, Colin. So Jim, can you give us a synopsis of what Colin said? Because I couldn't make it out.
Mainly he's saying he's done the measurements, but without seeing the plots, we don't. I mean, it's the easy to measure the effect, 10 to 20 dBs different at low frequencies, less of a difference at high frequencies. Whether it's important, it's all these other issues. The thing you said is really important, actually, fingered notes. String vibration parallel to the fingerboard under your finger, that's really not a good way of coupling stuff into the body. So,
well, I kind of done the experiment reciprocally. I was taking recordings of the bowed string musical excerpts and sending them to a driver so that you could put it on the wall and the wall is a speaker. You could put it on a box of cornflakes as a speaker. You could also put it on different parts of the violin and hear the relative sensitivity of the parts of the instruments. The answer was the bridge is here to stay. That's the place to drive it. But yes, you can make it make very violin-like sounds by touching it elsewhere.
But Jim, if I may just add one other thing. When you play a violin on a bowed note, you set up a Helmholtz motion on the bow. And there's a similar force, even though it absorbs more slowly in a sense, but it's still absorbed well enough to recreate that Helmholtz action. So it must be doing something in terms of exciting the.
The force is similar, but it's tangential to the fingerboard. It's not in a really good direction.
But any motion of the violin in any direction couples with every other direction, because it's a very complicated system, structural system, as we all know. So let's not worry about details, but there is an effect of the Helmholtz pulse hitting the finger, and that energy, or the force, is dissipated on that instrument and makes the instrument to vibrate. That's it. But whether it's important or not for the sound of the instrument and how important it is quite another matter.
Yeah.
Okay. Any other questions?
Nope, I don't see any other questions.
Thank you, everyone.
Can we wrap it up? All right, so thank you very much to our presenters, to Joseph, to Tom, and to Jim. We will we haven't done so, but we plan to schedule a series of these sessions over the next 6 months or so. So stay tuned, and you'll be on our mailing list. I have all of your emails if you haven't been already on our mailing list. So you'll get information